The worksheet concludes with a reaction for which quite a bit of data is available. One way to make butadiene, although not a modern method, is to heat cyclohexene to an extremely high temperature by passing the gas over a hot tungsten filament in the absence of oxygen. This generates 1,3-butadiene and ethylene. At room temperature, this reaction is both endergonic and endothermic. So at room temperature, cyclohexene is a very stable substance. From this data, we can calculate delta S, the change in entropy for this reaction. And for this, we will rearrange the equation delta G equals delta H minus temperature times delta S. This breaks the Gibbs free energy into enthalpy components, which is the heat consumed or generated, and the entropy component, which is a change in the degrees of freedom, or the energy dispersal. Please calculate the value of delta S before coming to class. Scrolling to the bottom of the page, we will now consider the reverse reaction. You will recall that I've emphasized since the first day of class that all reactions are reversible. And here we have experimental information on the reaction in both directions. As was introduced earlier in the worksheet, the reaction of 1,3-butadiene with ethylene does require forcing conditions. It doesn't require a hot tungsten filament, but it does require high pressure and between 170 and 180 degrees Celsius. So please come to class having calculated delta G for the reverse reaction, which is actually a forward Diels-Alder cycloaddition. But please calculate delta G at a temperature of 450 Kelvin. Then turn to the last page of the worksheet. The previous page of the worksheet was on thermodynamics, the equilibrium or how far a reaction goes in either direction. The last page of the worksheet focuses on kinetics. How fast is the reaction? And from the rate of the reaction, we get a direct sense of the energy barrier, which is delta G double dagger. That is the energy of the reaction coordinate at the transition state for the reaction. We won't derive this equation in this class, although you will probably have an opportunity to do that in a 300 level chemistry course. But if we know the rate constant at specific temperature, we can calculate the free energy of activation, the energy barrier for the reaction, delta G double dagger. This rate constant is a small number. This is a slow reaction even at relatively high temperature. And so it's not surprising to me that the energy barrier is relatively large, 160 kilojoules per mole. Using the thermodynamic information on the previous page and the kinetic information here, we will together in class draw a reaction coordinate diagram for the Diels-Alder cycloaddition of 1,3-butadiene plus ethylene at 450 Kelvin. Try this on your own before coming to class, and then think about what the reaction coordinate diagram may tell you about the energy barrier for the reverse reaction. This is the reaction of cyclohexene to give 1,3-butadiene and ethylene, but at a lower temperature, well below the temperature of a hot tungsten filament. This concludes the videos for Module 4A.